Okay, and now we can go. All right, so last time we essentially finished telling the story about the microcanonical ensemble. And now, next thing we want to do today is to introduce the canonical ensemble, which is also the most popular and used ensemble in statistical mechanics. So how to introduce the canonical ensemble? Well, the difference between microcanonical and canonical ensemble is essentially the difference between a system that is in conditions in which you fix the variables energy, volume, and number of particles to describe thermodynamics, and a system in which you trade the energy for temperature. So temperature, volume, and number of particles. And we know very well that energy is traded with temperature whenever, instead of considering a system that is thermally isolated, and therefore that is closed and cannot exchange energy with anything else, we consider a system that is open and can exchange energy with the external environment, with a huge external environment that in turn sets its temperature due to the conditions of thermal equilibrium. All right, so just a second, because I have to do one thing. Just 1 second. Okay. All right, so how to describe this situation? Well, let's imagine that we have a big system that overall is isolated, okay? So a big volume V with a large number of particles that is thermally isolated from the external environment, as represented by these lines that, well, so means that it's isolated. And now let's imagine that we split these systems into two subsystems, as we have done before to describe thermodynamics, a subsystem of volume V1 and a subsystem of volume V2 that is much larger than V1, okay? And in particular, as before, we want the energy of the two subsystems to be, their sum to be between E and E plus 2 delta. We know very well that the phase space volume gamma phi is going to be the product of the phase space volume at E bar 1 and phase space volume at E bar 2, as we have already found when I was discussing the Boltzmann formula for the entropy. And the conditions to find E bar 1 and E bar 2 are that the derivative of the entropy of system number 1 evaluated at E bar 1 should be equal to the derivative of the entropy of system number 2 at E2 evaluated at E bar 2. Okay? Now, in particular, we are going to assume, because these two volumes are very different, that the number of particles in 2 is much larger than the number of particles in 1. The volume V2, as I already said, is much larger than V1, and the energy E2 is much larger than E1. Okay? Now, formally, I can write gamma phi as being equal to the integral between E and D plus 2 delta, E1 plus E2, dQ1, dQ2, sorry, dQ1 and dP1, dQ2, dP2. Now I can rewrite this integral formally in the following way. I can write it as an integral over dQ1 and dP1 of the integral over E minus E1 smaller than E2 smaller than E minus E1 plus 2 delta dQ2 dP2. You agree? You agree with me, guys? So are you there, by the way?
Yes.
Okay, I'm not talking to myself.
Okay.
Okay. So now this integral here, sorry? Yes.
Yeah. The first integral. What is the limits of the first integral?
No limits.
No.
I'm integrating over the entire phase space.
Mm-hmm.
But I'm limiting myself in the second integral to these things. Okay? So I'm essentially, when I integrate over the entire phase space of system number 1, in system number 2, I have to integrate only over those configurations such that E1 plus E2 is in between the two limits. You see what is the point? So it's as if I'm asking you to integrate over all configurations such that x plus y is equal to 1, right? So I can integrate over all x and then integrate over y, imposing the condition that y is equal to 1 minus x. You see?
Yeah.
So that's what I'm doing. Anyway, this integral here, I call it gamma 2 of E minus E1, which is in principle a function of Q1 and P1, right? The energy of system 1 depends on the phase space configuration of system 1. And let's call this rho of E Q1 P1. So why I call it rho of E? Because essentially this tells me, if I rewrite it, that this is equal to the integral dQ1 dP1 rho of E Q1 P1. And this rho of E essentially represents the density in phase space of points in the restricted phase space of system 1 that are consistent with the conditions of having the total energy constraint. It's as if I'm projecting everything on system 1 in a sense. And now the question is, what is the expression for rho of E? Well, I know that rho of E, as I told you before, is equal to gamma 2 E minus E1 Q1 P1. Now, the point is the following. The total E is essentially dominated by what is happening in the system 2. because system 2 is much, much larger than system 1. And therefore, total E is much, much larger than E1. You see? Because V1 is much smaller than V2. Therefore, I can expand this in a power series. And what I'm going to get is the following. I'm going to get that K Boltzmann log of gamma to V minus U1 is equal to K Boltzmann log of gamma 2 of E minus E1. And then I'm going to have the derivative with respect to E of this quantity of S2, or of, let me write it like this, of K Boltzmann log of gamma 2 of E. Now you see that this quantity here is the entropy of system 2, S2 evaluated at E. Well, this is the derivative of S2 with respect to E. But this is equal to 1 over T, right? And therefore, what I discover at the end of this calculation is that the expansion of this is S2 of E minus E1, which is a function of Q1 and P1, divided by here we encounter the fact that sometimes I put K Boltzmann, sometimes I don't put K Boltzmann, and therefore everything is extremely confusing. I think it's okay. Given by this formula here. Now, what I'm going to do is I want to find rho of E, Q1 and P1. And this is equal to the exponential, if you look at the previous formula, of S2 of E divided by K Boltzmann minus E1 Q1 P1 divided by KBT. In other words, what I discover is that the density in phase space of system 1 is proportional to exponential of minus the energy Q1 P1 divided by KBT. Now, this is a density, is a projected, it's as if you take an hypersurface of the total system, then you project everything on the subspace of system 1, and then you look at the density of points in the subspace of system 1, and this is the density is going to be given by this expression here. Now, I could see this as a density, or I could interpret it as the probability. I could express this, interpret this expression here as the probability that probability density in phase space of having a system, of observing a system in the neighborhood close to the Q1 and dp1. Now, if I interpret this as a probability density, oops, no. Now, if I interpret this as a probability density, what I have is that whenever I want to compute an expectation value of some function f in phase space of Q1 and P1, well, so the expectation value of this function is going to be given by the integral dq1 dp1 of e to the minus. Let me now introduce the Hamiltonian. So h q1 p1 divided by kbt times f of q1 and p1. And of course, I have to normalize everything by this integral here, dq1 dp1 e to the minus h divided by kbt. All right, so up to here, I think it's something you have already seen and it's quite clear to everybody. Now, in particular, I could be computing using this expression all moments of the energy. So I could compute the average energy.
Professor?
Yes?
Can you please read the, okay, yeah. I want the page for your voice.
You wanted me to turn the page. All right. So tell me when I can move on.
Professor.
Yes.
Why you this? What's the reason you decide that this is the probability density?
Well, look, it's if you think about the frequency interpretation of probability, right? So I told you at the beginning that when you take the equal a priori probability, so the Boltzmann formula is based on the equal a priori probability postulate of statistical mechanics. That tells you that if you pick the hypersurface of constant density, sorry, the hypersurface of constant energy, or the slice of almost constant energy, the famous lasagna, then the density of phase space points there is uniform. Okay, if I do that experiment of having many systems with the same microscopic conditions and making microscopic measurements, the density on that hypersurface is going to be uniform, or in other words, the probability density is uniform. All microstates consistent with the macroscopic conditions have the same probability to occur. So now what I'm saying is the following. When I project everything or restrict all the integrals to the phase space volume of a subsystem, which is much smaller than the entire system, I can write this as the integral dq1 dp1 times this density. Now this is what? Rho of E is the projected density on the subsystem. It's as if, let me make an example. You take a three-dimensional density or a three-dimensional object and you project it in 2 dimensions. And when you project it in 2 dimensions, for example, if you have a cube, you will have 2 surfaces that are, projected on the same space. And of course, when you superimpose them, your density is going to be higher. You see? And now what I'm saying is that I can now go back and interpret this rho of E as the probability that a phase probability density to observe my subsystem, not my entire system, my subsystem in a phase space volume dq1, dp1. Why? Because essentially, when I look at this neighborhood, this rho of phi tells me how many, tells me roughly how many instances on the original big phase space I have that are projected there. I don't know if I explained it. This is not very easy to explain on a the image you should have in mind is the following. So let me try to explain it with an image. Suppose that I have an hypersurface of this type. Okay. And here, this hypersurface is covered uniformly. And now I project everything in this direction. So my restricted phase space is this plane, this one. Now you see that for certain points, the points on which I have this wiggle, I have actually a darker projection here because I have more than one way, actually 3 ways in the original system to end up here. And therefore I will get a higher probability to observe the system in that little slice. And for example, instead up here, I have just one way because there are no other points on the surface. And therefore, when I project on a plane or on a subsystem, my uniform distribution of the entire system becomes a restricted distribution that has a structure. And what I'm saying is that this structure is exponential in H1. Is it clearer now? Yes or no?
Why the structure is exponential?
Well, the structure is exponential because I proved it here. If you don't do the calculation, there's no way to guess.
So this is the projection on that hypersurface, and
yes,
it's you can say it's proportional to the exponential.
Yeah, absolutely. That's the point. It's proportional to the exponential of U1.
Okay, thank you.
All right, so now when I look at this formula here, you see that I can use this formula to calculate, for example, all moments of the energy, right? H squared, etc., etc., etc. When I calculate, for example, the first moment of the energy, average energy, well, this is equal to the integral dq1 dp1 e to the minus beta h, beta is 1 over kBt, h divided by integral dq1 dp1 e to the minus beta h. And therefore, this is equal to minus 1 over beta, the derivative with respect to beta of the log of the integral dq1 dp1 e to the minus beta h, right? So that justifies, in a sense, the introduction of a special of an object z, which is equal to the integral dq1 dp1 e to the minus beta h q1 p1 which is called the partition function. All right.
Sorry, Professor.
Yes.
So when we started looking at a system that having about two different coordinates, if you may, the Q1, the P1, the Q2, the P2, and as we've proved, it turns out that our partition function, the Hamiltonian, and all are depending only on the coordinates of one of the systems, one of the partitioned section of the system we considered. And I'm sorry if you could go back to to where we started. Yes.
Here.
Yeah. And
yes.
this is only depending on the smallest the coordinates of the smallest section of this. Yeah, I mean, I was even though I agree that I've seen the mathematics, it's clear that this depends on one of the sections, but I was expecting that since V2 is much more larger, one should expect that it should depend on the coordinates of the second section.
Well, it does, right? Here I'm doing the integral over dq2 and dp2. Of course it does depend on q2 and p2, but I'm integrating explicitly over that, right? So of
Yes.
course it does depend on q2 and p2.
So
I'm integrating, yeah, so
I could also do in the same way, only integrate in this integral, only start with dq2,
well, yeah, you can do that, but then there is a problem. I'll tell you what is the problem. Of
Okay.
course, you can do the opposite. You can integrate over dq2, dp2, and then integrate explicitly in here over q1 and p1. But then the problem is that you will get something of this type. Rho, instead of rho of phi q1, p1, you would get here rho of phi q2, p2, which is equal to gamma 1 e minus e2.
Yes.
Okay.
Yes.
Now, what is the problem now? The problem is that E2 is much larger than E1,
Yes.
right?
Yes.
And therefore, this is comparable to that, right? And therefore, you cannot do this expansion. You cannot do it.
Oh, I see. Okay.
Doesn't make any sense. So you see, the construction is made in such a way as to have here E1 that is much smaller than E
Okay.
by construction.
I see.
So
Thank
that's
you.
the point.
Thank
It's a
you.
very important point. It's a good question, actually. All right. So here we are. We call this the partition function. Now look at this formula here. When I wrote this, you should be very upset seeing this formula. I'm surprised that you didn't start shouting at me when you saw it. Why is it upsetting?
I'm thinking the section of the the Q1, the P1, if we take that they won't be dimensionally stable, I guess, maybe.
What does it mean dimensionally stable?
I mean, we are
To be
expecting the
dimensionally
energy.
stable.
We are taking the average of Hamiltonian. We expect it to to have the
No,
same
no, that
dimension.
is that is fine because here I have KBT. No, wait a second. Then I have a derivative. No, it's actually something deeper than that. In a log, can you put an expression like this in a log?
No.
No. Why?
Yeah, because logs is actually dimensionless
Exactly, because it has to be dimensionless. Therefore, also here we have the same problem we had before, that we have something dimensionful and we don't want it to be dimensionful. Therefore, as before, we have to normalize this. We normalize it by h, some constant to the power 3n, the constant has dimensions of an action. And typically, you also normalize it by n factorial. This is what is written in all books. Now, there is no way to understand where this all n factorial comes from unless you use quantum statistical mechanics. So let's put it there. Let's put this normalization there, and we will come back to justify it when we will do quantum statistical mechanics, so later on in this course, okay? All right, so given the fact that we have this normalization now, what can we say about our system? Well, first of all, when I write an expression of this type for a partition function or whatever, so now, since I know how to interpret this as a probability density, I know how to compute averages of all kinds of functions in phase space. But what I want to do when I do statistical mechanics is thermodynamics, right? I want to use microscopic physics to derive macroscopic properties. Therefore, as we have done for the microcanonical ensemble, in which we started with a system that was described by Newton equations, and with the Boltzmann formula, we figured out how to compute the entropy. Here we should figure out how to compute some thermodynamic potential using, for example, the partition function. Now, in the canonical setting, the connection between the micro ward and macro ward comes through the following formula. So this connection comes through the formula Z equal to e to the minus beta times f. You see? So the connections comes through stating that the partition for the Helmholtz free energy is equal to minus kBt log of Z. This is the connection between microscopic physics and macroscopic physics in the microcanonical setting. And now the first thing we have to do is to prove that this connection is actually meaningful. So how do we prove it? Well, essentially, just a second. Essentially, we have to prove the following. We have to prove that this makes sense, considering the fact that in thermodynamics, we know what is the Helmholtz free energy. the Helmholtz free energy is U minus T times S. And we also know that since this can be written as U plus T dF dt at constant volume, right? Or this implies that the average energy, which is also the internal energy, U, should be equal to F minus T dF dt at constant volume. Okay? Therefore, if this expression is correct, I have to obtain that when I compute the average energy, this is given by F minus T dF dt with the expression of the free energy given by this formula here. This is fundamentally important. If I don't verify this equation, then, well, there's little chance that my connection between the macro and the micro is correct. All right, so let's prove this formula. Proof. The proof goes as follows. First of all, the formula Z equal to e to the minus beta f is can be written as e to the minus beta f equal to the integral dq dp h over 3n n factorial e to the minus beta h. Now, this means that the integral dq dp over h to the 3n n factorial e to the minus beta h minus f is equal to 1, right? I'm just taking e to the minus beta f on the other side. Now, if this is equal to 1, then clearly, if I take the derivative, then take the derivative on both sides with respect to beta, I will get 0. Right?
Yes.
And now, let's see. Let's see what happens when I take this derivative. The derivative is integral dq dp over h to the 3n n factorial. Then I will have minus h plus f plus beta d beta f e to the minus beta h minus f. And now, since, let me write it here, beta d beta of something is equal to minus t dt, then this can be written as being equal to the integral dq dp over h to the 3n n factorial of e to the minus beta h minus f minus t dtf minus H equal to 0. And therefore, you see that this implies, well, so this term here, f is not a function of q and p, right? So therefore, this term here is f minus t dtf times integral dq dp divided by h to the 3n and factorial e to the minus beta h minus f minus average of h. But this is equal to 1. And therefore, what I discover is that I have exactly the formula that I wrote down before. You see? So the average energy is equal to F minus dt, T dF dt. So therefore, this is the free energy, is an appropriate definition for the free energy. And once I have the Helmholtz free energy, I can reconstruct the rest of thermodynamics. I can compute P, which is equal to minus dF dV at constant temperature. I can compute the entropy, which is equal to minus dF dt, constant volume, etc., etc. I can calculate whatever I want. Okay? Are there any questions at this point? All right. So now, an important thing you might ask yourself is whether what we have done up to now is so whether using, let me say it in a different way, whether using the canonical or the microcanonical ensemble makes any difference for calculations in statistical mechanics for the final results. Okay, I said that we are fixing different thermodynamic variables, but you know the real question is, if I use the canonical ensemble to compute the average energy of a system, or I use it to compute the equation of state, do I expect to get something different as compared to the microcanonical ensemble?
No.
Now the answer, yes?
I said no, no difference.
No, we don't, exactly, we don't. Why?
Because the limit of thermodynamics is the same.
The limit of thermodynamics is?
The same in the two cases.
Can you make this statement more precise? What do we have to prove in order to show that the two give the same result? That the two are equivalent. What do we have to prove in order to show that the two are equivalent? In the thermodynamic limit, as you correctly said, in the thermodynamic limit, they are equivalent. What do we have to do in order to prove it? Is there someone who has an idea? How do we prove that the two ensembles are equivalent in the thermodynamic limit? Well, so in the first ensemble, yes?
We can take a limiting case of of the volume and the number of particles, I think.
Mhm.
Approach it to infinity, I guess.
Yes. Okay. And show what?
Show that the, I guess there's some equivalent statement, like both of them are equal in those limiting values.
What does it mean to be equal?
Sorry?
So
Sorry.
what? There are many ways to be equal, right?
Mm-hmm.
What does it mean to be equal?
No, the limit. The limit should be equal, I guess.
Okay, so let me try to do it in the following way. In one ensemble, we are fixing energy, volume, and number of particles. In the other ensemble, we're fixing temperature, volume, and number of particles, and the energy can fluctuate. Okay? Now, if I now prove that, so this is the microcanonical, and this is the canonical. Now, if I now prove that in the canonical ensemble, when I compute the average energy, E, so the average energy is going to be an average function, right? But there are going to be fluctuations because the energy can fluctuate in the canonical ensemble. I can find sometimes an energy E, an energy E plus delta, E plus whatever, E minus whatever. It's going to have a certain probability distribution. Now, if I now prove that this probability distribution in the thermodynamic limit becomes extremely narrow and goes towards a delta function. So in other words, it's strongly peaked around the average energy with negligible fluctuations. And it's evident that the microcanonical and the canonical ensemble in this limit are equivalent, right? Because the energy can formally fluctuate in the canonical, but the fluctuations are small in the thermodynamic limit. So it's practically as if it didn't fluctuate. You understand? So, in other words, the equivalence of the two ensembles comes through showing that the quantity that you let fluctuate in the microcanonical ensemble, in the canonical ensemble, as compared to the microcanonical ensemble, has actually fluctuations that are negligible in the thermodynamic limit. So that's the statement. So how do we prove this? How do we prove this equivalence of ensembles? Well, let's go through the definition again. What is the average energy?
Is that hyperprobable? Hyperprobable. I mean, the average is the highest frequency for something to happen.
This is not, well, it depends, right? If you have a Gaussian,
when
yes,
the fluctuate is not negligible.
Okay, look, in probability, in general, the average is not the most probable value, right? And that is clear. If I give you a distribution of this type, probability distribution that looks like this, well, the average is probably going to be around here. But the most probable value is this one. Now, the statement I'm making here is not that is not that the average is the most probable value. What I'm saying is that in the thermodynamic limit, as we will see, the distribution function becomes strongly peaked around the average value. It's actually a Gaussian, as we will derive later on. It's strongly peaked around the average value with a standard deviation that is actually tending to zero if as compared to the average in the thermodynamic limit. That's the statement I'm making. Okay? Can I go on?
Yeah.
Okay. So let us first continue computing the average energy. All right, so the average energy, which is equal to U, is equal to integral dq dp h to the 3n and factorial e to the minus beta h minus f. Okay? Times h. You agree? Therefore,
Yes.
therefore the integral dq dp h3n and factorial e to the minus beta h minus f h minus u is equal to 0. Let's take now just a second. Let's now yes, let's now take a derivative of this expression here. So what we get is the following. We get that du d beta plus integral dq dp. So when I write dq dp with this parenthesis, I mean the dq dp normalized by blah, 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 times u minus h times f plus beta d beta f.
Sorry.
Yes?
In the second line, is it just minus u or u multiplied by this integral?
Is it which second line? Oh, of course, is u multiplied by the integral. Of course, is u multiplied by the integral. Of course.
No, because u is equal to this integral times h. So if we substitute.
No. Wait a second. You agree? So it's u multiplied by dq dp over h to the 3n and factorial e to the minus h minus f times beta. And now the point is that this is equal to 1 by definition. You see?
You mean the average of h is u times this integral?
No. What I mean is the following. Let me do it slowly. What I mean is the following. I can rewrite this expression as u times integral dq dp over h to the 3n and factorial e to the minus beta h minus f equal to this stuff here. Equal to this. Right? You agree with me?
Yes.
Because this is equal to 1. And therefore now when I take it on the other side, when I take this on the other side, you see that I can rewrite this as integral dq dp e to the minus beta h minus f h minus u equal to 0. Okay? So that's how I get there. And now I'm just taking a derivative of this, which is this expression here. So, of course, the derivative should be equal to 0. But now let's look at what I wrote here. This is u minus h. And this is actually, if you go through what I wrote down before, this is again u minus h. Why? Because u is equal to f minus dt f dt, but minus dt f dt is plus beta d beta f, and therefore this is again u, this one, minus h. Therefore, what I discover is that this is equal to d beta u plus integral dq dp of u minus h squared e to the minus beta h minus f. Okay? Therefore, this is... Yes?
Can you return just for 1 second? To
Here?
Yeah. Nice.
Okay. So this is d beta u plus average of u minus h squared equal to 0. But u minus h squared, this is what? Is u squared minus plus h squared minus 2uh, where u is equal to average of h. So you see that the average of this is equal to just 1 second, is equal to average of h squared minus average of h squared. In other words, is the average of the fluctuations. So at the end of the day, what I discover from this formula is that the fluctuations of the energy are equal to minus d beta u. But d beta u is t squared dt u. And this is t squared times the specific heat, the heat capacity. The heat capacity is an extensive quantity. It's not like the specific heat, which is normalized, which is intensive. This goes like N. And therefore, this implies that if I take the square root of this and compare it to the average energy that, of course, scales like N, I obtain something that scales like 1 over square root of N, right? because I have square root of n divided by n, and I obtain overall 1 over square root of n. And this goes to 0 in the thermodynamic limit. Therefore, in the thermodynamic limit, the fluctuations of the energy are much, much smaller, are essentially irrelevant or as compared to the average. Now, this is not surprising. It should not be surprising what I'm saying. Actually, we already know that this is what should be the case. And we know it from a theorem that is among the first things we proved in this course, that is called the central limit theorem. What we are saying here is something extremely simple. The energy is an extensive quantity, right? And therefore is additive. The energy of the total system is equal to the sum of the energy of its components. Right? So suppose that I take a very big system, I divide it into subsystems, some smaller components, and compute the average energy into each one of these subsystems. And of course, the energy is going to be the sum over all the energies. Now, if in each individual subsystems I have a certain probability distribution of the energy, and all of them are identical and they are independently distributed, it's clear that in the limit where the number of components becomes very large, the probability distribution of the total energy is going to be, because of central limit theorem, a Gaussian distribution with a width that scales as compared to the average as 1 over square root of n. This is exactly what we found when we proved the central limit theorem in the second lecture of this course. Okay? So it's not surprising that the two ensembles are equivalent. Actually, if we go deep into the origin of this equivalence, it's connected to the fact that the two are so to say, I mean, the energy is an extensive quantity. That's essentially the reason. All right, so now to finish, I want to show you how to prove this in a slightly different way that is actually quite interesting and useful. I want to get an approximation or to get a feeling of how the probability distribution of the energy looks like for this system. In order to do this,
Professor.
Yes.
I still don't quite get the point where you say, finally we prove that it's equal in the thermodynamic limit.
Yes.
Which one that actually prove that it's equal in the thermodynamic limit?
Well, if the fluctuations are much smaller than the average, right? So
the fluctuation is the delta.
Yes. If square root of delta H squared is much smaller than average H in the thermodynamic limit, this means that the greatest, with almost one probability, any system you pick up with those conditions is going to have an average energy E. The variation are going to be negligible in the thermodynamic limit. And therefore, they are practically equivalent. Fixing the temperature or fixing the energy is practically equivalent in the thermodynamic limit. You see?
Fixing temperature and fixing the
energy are practically equivalent in the thermodynamic limit.
Oh, okay.
Okay. All right. So now this other proof of the same story. So what do? Let's try to get the probability distribution of the energy. So in order to get P of E, the probability to have a certain energy E, what I have to do is to compute the integral dq dp of delta E minus H times e to the minus beta H divided by, normalized by the partition function. So let me normalize it by Z. So let's forget for a second about this normalization and just look at the integral above. Now this integral above is integral dq dp delta E minus H e to the minus beta. Well, since I have a delta function, I can substitute it here, delta of E divided by Z. Now this is equal to, now integral dq dp delta E minus H, well, I can write it as E beta T, or, well, I can write it as omega of E is essentially the derivative of sigma. If you remember, the phase space volume contained in the hypersurface of energy E. So it's omega of E times e to the minus beta E divided by Z. And this I can write as e to the beta T log of omega of E minus E. Or in other words, e to the beta S of E times T minus E divided by Z. All right, so this is the probability distribution. And now let's look closely at this probability distribution. What we are dealing with here in this exponential is with functions S of E that are extensive functions. What does it mean is that in this exponential, there is a big prefactor that scales like n. It's like a function it's like a function e to the minus n times some f of x. Now, a function of this type has the following property. If f of x looks like this, right? Looks like this. It's a function that has a minimum at a certain value x star. Then the probability distribution e to the minus n times f of x is going to look like this. It's going to have a value here. It is exponential of minus f nf at x star. And then is going to be strongly peaked around this value. Why? Because any deviation from the maximum value is going to be exponentially smaller than the optimal value. Let me explain it in a different way. If I take f of x and I expand it around x star, I will get f of x star minus, because it's a minimum, f double prime of x star divided by 2. Sorry, plus f double prime of x star divided by 2x minus x star squared. And f double prime is going to be smaller than 0. Okay? Then you see what happens. E to the minus n f of x is going to be approximately e to the minus n f of x star e to the minus n f double prime sorry, f double prime is a minimum, so it's a, this is greater than 0. I apologize. F double prime of x star divided by 2x minus x star squared. Now you see what happens. If x is not equal to x star, then you see that here I have exponential of minus n times something positive. And therefore, in the limit in which n is large, if I compare e to the minus n f of x to its maximum value, this is exponentially decaying to 0. Okay? So in other words, this probability distribution has this maximum value, and then all values away from the maximum are exponentially smaller than the maximum. It's essentially a highly peaked probability distribution. In practice, it's a Gaussian, you see? It's a very nice Gaussian with a width that scales like 1 over square root of n, as I mentioned before. Now, this is, by the way, the basis of a method that you use to estimate integrals that is called the saddle point method. We will be using it later on. So all this logic is the basis of this saddle point method. So now, what I wanted to say now is the following. I have this, and now let me look at this function and try to find what is the, so both E, S, and E are scaling with the volume. Let me try to find the extrema of these functions. So let me copy this. P of E, I said, is proportional to e to the beta t s of E minus E. All right, so the extrema of this function, well, I just take a derivative with respect to E. What I get is that the condition that I asked to satisfy in order to be an extremum is that t times the derivative of f's with respect to E at E star should be equal to 1. And therefore, not surprisingly, I have the usual condition of thermal equilibrium that the S, the E at E star should be equal to 1 over T. It's always the same story. Now, in addition to this, since here I have a plus sign here, I have to have that the second derivative of this function should be negative because I want to have a maximum instead of a minimum. All right, so what is the second derivative? Well, the second derivative of the function there is d squared s dE squared times t, and this is equal to dE of 1 over t is equal to minus 1 over t squared dt dE, constant volume, and this is equal to minus 1 over t squared times CV. Therefore, I have that the second derivative is negative, as I wanted, and in practice, I obtained that this is approximately e to the beta Ts of E star as determined by the condition of equilibrium minus E star times e to the minus E minus E star squared divided by 2t squared CV. And now you see again what I mentioned before. The probability distribution of the energy is approximately in the thermodynamic limit a Gaussian with a width that with a standard deviation that is actually as compared to the average. E star, by the way, is the average energy, and you see that E star is going to be, of course, extensive, and the width scales like CV, square root actually of CV, so scales like square root of n. Therefore, when you compare the two, you will get that this Gaussian becomes strongly peaked around the average value in the thermodynamic limit. So it's the same story I told you before, told in a different language, looking directly at the probability distribution of the energy. All right, so I'm essentially done for today. Next time we will be starting to solve a few exercises on the canonical ensemble. So practically we will do free spins, free set of spins, we will do the ideal gas, etc., etc., etc. Yes.
Professor?
Yes.
You said that this is the same story as before. Where do you find the 1 over square root of n?
Here. You see that there is t squared CV. It scales like n. When I take, so when I have e to the minus e minus e star divided by 2 CVT squared, I obtain in that formula. You see that this CVT squared, this is e minus e star squared divided by 2 delta H, right? And now you see that the width of this thing is actually the square root of this number. And therefore, when you compare the width to the average, as I've done here, you obtain that it scales like 1 over square root of n.
Oh, which width?
Well, if you compare the width of your Gaussian, which is square root of t squared, the sigma of your Gaussian, how's it called, the standard deviation, no, I'm always confused. The standard deviation of your Gaussian, which is the square root of t squared CV, you compare it to the average, you get that the ratio scales like 1 over square root of n, as in this case. Okay?
Okay.
All right, guys. So I'm going to see you then on Friday, and we will start solving exercises with the canonical ensemble.
Professor,
Okay? Yes.
I have a question.
Sure.
Do we have a tutorial or something?
I have to organize it, to be honest. I mean, the fact that all this COVID is making my life a bit complicated, but I will try to organize it for you. Okay?
Oh, okay.
If you want tutorial.
Yes.
Actually, the
appreciate-
person I had last year for tutorial is unfortunately abroad now, so we have to find someone else. I will. Okay, no problem.
Thank you.
Thank you.
Okay. Okay, guys. I'll see you on Friday then. Bye-bye.
Bye.
Bye.